Good afternoon everyone, myself Moma Samanto. I am your NPTEL PMRF teaching assistant for this course starting from July 2026, and the course instructor is Professor Sripad Garg from IIT Bombay. So this is our week 3 tutorial discussion session, and before starting or going towards solving some problems, I would like to know if anyone has any doubt from previous assignments or previous lectures. You can let me know, then I will try to explain those doubt fast, and after that I will start solving some problems related to the topic based on the lectures up to week 3. Okay, so I will wait for 2 or 3 minutes. If you have any doubt, just turn on your mic and tell me one by one. So Kamaljeet, you turn on your mic and then just let everyone know. So is there any problem in turning on mic from your side?
Yes, ma'am. Yes. Question number 6. I have a problem in assignment 2.
Okay, question number 6 in assignment 2. Okay. So can you just tell me what is the question? Then I will write it down and try to.
Okay, question is let Qn be a polynomial in one variable with integer coefficients and p be prime.
Let Qn be a
Polynomial in one variable.
in one variable
With integer coefficients and p be prime. Then we are taking tuple like Qn comma p is admissible if p is the smallest prime.
Okay, this is called admissible
If p is the smallest prime of the form Qn. For some integer n.
So what is the question?
Now question is which of the following pairs is or are admissible?
Okay, so what were the options here?
Here the first option is nq minus 1 comma 3. Second one is n square plus n plus 4 comma 2. Third one is nq minus n plus 1 comma 7
nq minus n
plus 1.
Okay, plus 1 and 7. Okay.
Then fourth one is n square plus 1 comma 2.
Okay, so what is your doubt here?
Ma'am, actually I have not understand the question here. What we can do.
Okay, okay. So you did you get that definition of admissible? This one. So it is saying that what is Qn here? Qn is just a polynomial function or polynomial function in one variable which is taking the input n, that means natural integers or natural numbers you can say, and the coefficients of this polynomial function is are integers. Now it is saying that this pair is called admissible if p is the smallest prime. So what you have to do in this question, since this is multiple multiple options are correct here and some options are given, you can check whether putting the values of n from 1 up to 1 to up to like that, you get this kind of pair or not. So for example, say here in this first option, what you have to check? You have to check whether we can get some smaller prime than 3. Which prime is the smaller than 3?
2 is
Only 2 is
the
there.
that prime
So
to
you have to check for any integer n whether we can get the prime 2 in this first option. Okay, if we cannot get 2 here, and we get what we have to check for, say for example 1. Okay, so for first option you just check if there exists some n belongs to z such that n cube minus 1 equals to 2. If this exists, if this some particular n exists, then what we can say? We can say this pair is not admissible, because this pair is saying 3 is if it is is admissible, then this 3 has to be the smallest prime. So if we can get that if there exists some n such that this equality holds, then we can nullify this option. That means we can say this is false. Or if we if we want to show that this option is correct, then what we have to show? We have to show simultaneously that there does not exist any n belongs to z such that n cube minus 1 equals to 2, and there exists some m belongs to z such that m cube minus 1 equals to 3. So we have to check this to show that that pair is admissible, or we have to show this one to show that this first option is not admissible. Okay, so you have to check in this way for every for all those 3 options. For example, if we take n equals to, so can you suggest me if we can get some integer n such that n cube minus 1 equals to 2? Can you get? If we take n equals to 1, it will give us 0. If we take n equals to 2, that will be greater than
3, that will be 7.
Greater 7. That means that will not give us anything like 2. If you take negative integers, then also you will get negative numbers. You cannot get 2 or you cannot get 3 also, right?
Okay ma'am, okay.
So in this way you have to check for every options. I hope for some smaller integer you will get value of n such that some of these options hold true. Okay.
Okay ma'am, thank you.
So your doubt is clear, right?
Yes ma'am, yes.
Okay. Anyone else? Denmoji, R and Ganga, do you have any doubt?
No, ma'am.
Okay, okay. So let's start our discussion today then. So do you remember what I have if you have joined in week 2 tutorial session, you can find that I was asking some questions and said that if you get that answer, then just tell me, or if you cannot get, then I will try to prove that. So what was that question? That question was, we all know that for two integers a and b, if GCD of AB equals to D, then we can write D as linear combination of AB, that is A alpha plus B beta for some alpha beta belongs to Z. Now we said that this pair alpha beta, this is not unique. What does it mean? This means that, so what we tried to show, the elements alpha beta belongs to Z are not unique. That is, that means there exist alpha prime beta prime belongs to Z such that D equals to A alpha prime plus B beta prime equals to A alpha plus B beta. Alpha beta belongs to Z, and what we can say, alpha not equals to alpha prime, beta not equals to beta prime. So this is the statement we want to prove. So did you get the answer? Any one of you? If no, then just say no, then I will try to show. Just type no at least. Kamaljeet? Okay, you know. And Ganga? Okay, so let's try to prove it. So what we want to prove is that, so we know, you all know this expression, right? This expression is already known. It is proved in lecture video by professor. So what we will show? We will show that there exists some alpha prime beta prime rather than alpha beta such that D equals to A alpha prime plus B beta prime. So let's start. So we all know that at least one solution will exist. There exists some alpha and beta such that D equals to A alpha plus B beta. So let us, what are the informations we have? A, B belongs to Z, and GCD of AB, B equals to D. Then there exists some alpha beta belongs to Z such that D equals to A alpha plus B beta. Now my claim is, there are infinitely many solutions of the equation Ax plus by equals to D. So So given that alpha beta is a solution of this equation, then we can claim that this ax plus by equals to d will have infinitely many solutions. That means there will exist infinitely many tuples xy such that this xy satisfies this equation. And in particular the solutions will be, and the solutions are x equals to alpha plus b by d times k, and y equals to beta minus a by d times k for some integer k. Okay, so do you understand why I am saying how I am saying that this is not unique expression for d? So if this equation has infinitely many solutions, I mean there are infinitely many tuple x comma y such that this equation holds, then this is the exactly similar thing to say d does not have unique expression. So now we will try to show this equation has these kind of solutions for not some, for any k belongs to z. Not infinitely many, sorry. The other solutions, not infinitely many, other solutions of the equation. Okay, let's try to prove it. So let alpha prime beta prime belongs to z such that d equals to a alpha prime plus b beta prime. So now already we have the expression for d like this, a alpha b beta, and alpha and alpha prime beta prime are some other solution than this alpha and beta, where okay. So what we have then? We have a alpha plus b beta equals to a alpha prime plus b beta prime, because both of this is also equals to d and this is also equals to d, therefore they are equal. Now we can write it in this way: a times alpha minus alpha prime equals to b times beta prime minus beta. Now what we have? GCD of AB equals to D. So in our second week tutorial session, I have proved one statement which says that if GCD of AB equals to D, then what will be the GCD of A by D, B by D? What will be that? Can anyone recall?
That will be 1.
1, ma'am.
1, it is 1. Therefore now I am saying that A by B, let us write, let A by B equals to R and B by D equals to S. Then GCD of RS equals to 1 we have. Now since GCD of RS equals to 1, say this is the equation star. From star what we can say? We get that A by D, this is D not B, that we can write, divide both sides by D, then what we will get? This is R times from star, dividing both sides. Okay, both side of star by D, what we get? We get that R times alpha minus alpha prime, this is equals to S times beta minus beta prime. Now use Euclid's lemma. We have GCD of R and S, this is 1. Therefore using Euclid's lemma, what we can say? What we can say? Tell me. If GCD of R and S equals to 1, so R times alpha minus alpha prime equals to S times beta minus beta prime, what will it imply? Can we say divisibility of R and beta minus beta prime? What was the Euclid's lemma? If, what was that? Just recall what is the Euclid's lemma. So R times this equals to S times beta minus beta prime, and GCD of R and S, this is 1. So this, so R times this equals to this, that means R times R is dividing this whole term. So let me write first, then I hope you will understand. So when we say that A divides B, when we say A divides B, if there exists R belongs to Z, there exists alpha belongs to Z, so, say A divides B if there exists U belongs to Z such that B equals to AU. Now see here R times this equals to S times beta minus beta prime. Then what can we say about divisibility of S and this whole term, or divisibility of R and this whole term? R times something equals to this term, that means R is dividing this whole term. Do you get it? We are saying from this expression, since R times some integer equals to S times this, therefore we can say R is dividing this whole term. In other words, say R times this is, take this as whole integer and this is equals to S times this integer. So therefore we can say S is dividing this whole term by this definition. That was the basic definition. So therefore here from this expression what we can say? We can say either r is dividing this whole term or s is dividing this whole integer. Okay, now Euclid's lemma is saying if AC divides BC and GCD of if A divides BC, what Euclid's lemma says, it says that if A divides BC and GCD of AC equals to 1, then by Euclid's lemma you can conclude A divides B. Okay, now we will use this fact in this case. So what we will write here then? So since GCD of R since GCD of RS equals to 1, we say using Euclid's lemma R divides beta minus beta prime, as GCD of R is equals to 1. So R divides beta minus beta prime, that means therefore beta minus beta prime equals to R times K for some integer K belongs to Z. So this is the definition of divisibility. So from here what we can say? Beta prime equals to beta minus RK. Okay, now substituting these to star, what we get? We get that, what are the star here? Star is this, not here, not star, this is a double star or hash. We get that there was R times alpha minus alpha prime equals to S times beta minus beta prime equals to beta minus beta prime equals to RK, that is alpha minus alpha prime equals to S times K, implies alpha prime I have done something wrong, right? What was that? Beta minus beta prime equals to RK. Oh, sorry. Here it should be beta prime minus beta. See here it was A times alpha minus alpha prime equals to B times beta prime minus beta. So what we should write here? We should write here beta prime minus beta. Okay, so R divides, here we should write beta prime minus beta, beta prime minus beta, beta prime minus beta equals to RK. Therefore beta prime equals to beta plus RK. Okay, beta prime equals to beta plus RK, and then alpha minus alpha prime, this is equals to beta prime minus beta, and this is equals to RK. So alpha minus alpha prime equals to SK, so alpha prime equals to alpha minus SK. So what we get? We get therefore, and what therefore the solutions r alpha prime equals to alpha, what was s? S was b by d times k, and beta prime was beta plus r was a by d times k for k belongs to z. So what we did, we have taken first, let alpha beta d has the expression a alpha plus b beta, then we are considering that let alpha prime beta prime, this is some another solution of that d, then we can say that this alpha prime and beta prime will have this form where k is some integer, k is coming from some integers. So for any value of k we will have this kind of solutions alpha prime and beta prime which are different from the given expression d equals to a alpha plus b beta. So therefore we can conclude thus the other solutions of what, which equation? 1 minute. So other solutions of ax plus b beta equal by equals to d are of the form x equals to alpha minus b by d times k, y equals to beta plus a by d times k for k belongs to z. So this is the thing why the solution is not unique. I mean the pair alpha beta are not unique. So here if you see that here I have written it as positive and this is as negative, but this is equivalent to write this is negative, this is positive, because if you take k as minus k as minus k prime, then you will get the signs, you can get the signs reverse here. I mean if you take the expression here negative, then you have to take positive here, and if you take positive here, then you have to take negative here. Okay, that is the only confusion. So this was the first question I had asked in second tutorial session, and this is the solution. So now let's try to solve some questions related to that prime. Okay, anyone has any doubt in this proof? If you have any doubt in any line, just tell me. Otherwise now let's solve the another question. So do you remember what was the definition of composite number? So let us recall, composite number was, it was if we can write r equals to a times b, for if we can write r equals to ab such that 1 less equals to a, no, not less equals to 1 less than a, b less than r, 1 less than a comma b, both are less than 1, greater than 1 and less than r, then we say r as r is a composite number. Now let's solve one question. Question is, if p is a prime greater equals to 5, then show that p square plus 2 is a composite number. Okay. So what we have to show? Given condition is p is a prime number which is greater equals to 5, and then it is asking us to show p square plus 2 is a composite number. That means p square plus 2 has the form a into b for two integers a comma b which are not 1 and not equals to that number p square plus 2. So p is a prime greater equals to 5. From here, one, can you give me one expression for p? I mean, p is a prime number greater equals to 5. That means p has to be an odd prime. Now odd primes have the form, odd integers have the very basic form, that is in terms of 2, residue class of 2. If you say, it has the form 2n plus 1, and if you take the residue class of 3, so what will be the form of a odd integer in terms of residue class of 3 is that okay, so since p is a prime greater equals to 5, p is a odd prime, then if you take if you take the expression of p, yes, Kamaljeet, you are right, that is the question I was asking. P will have the form either 3k or 3k plus 1 or 3k plus 2. 1 minute. Okay, Ganga, wait for 2 minutes because I will tell, it will not be 3k, I am just telling. Okay, so p can have one of these forms. Now if it is 3k, and if k is greater than 1, then this is a composite number. So, and now it is saying p is greater equals to 5. Since greater equals to 5, p cannot be 3, that means k cannot be 1. Therefore this condition is we cannot consider this condition. So only left conditions are, we can have the form of p as 3k plus 1 or 3k plus 2. Okay, so since this is a odd prime, and p has one of the forms 3k plus 1 or 3k plus 2. Okay. Now case 1 is when p has the form let. So then what will be the p square plus 1? P square plus 2. Okay. P square plus 2 is 3k plus 1 whole square plus 2. That means 9k square plus 6k plus 3. That means 3 times 3k square plus 2k plus 1. So this term is greater equals to 1. Sorry, not greater equals to, strictly greater equals to 1, because since this term is greater than 1, so 3 times something has to be greater than, 3 times something that has to be a composite number. So this was the definition of composite number. So it is saying R is a composite number if R equals to A times B, where A and B both are not equals to 1. So here p square plus 2 can be written as 3 times this integer, and this integer is always greater than 1 for any k belongs to, for any k belongs to n. I should write n. Where why I am taking it from n? Because p has the form this one, and p is a natural number. So if k does not belongs to natural numbers, this term will be negative, and p cannot be negative. That's why k belongs to n, and k has this form, p square plus 2 has this form 3 times this integer, and since this integer is greater than 1, we can say that p square plus 2 is a composite number. So in this case we are done. Now what is the remaining case here? The case is when p has the form 3k plus 2. In the similar way, you can see what will be the value of p square plus 2 here. Let p equals to 3k plus 2. Then p square plus 2 p square plus 2 equals to 9k square plus 12k plus 4 plus 2. That means we can write it as 3 times 3k square plus 4k plus 2. And similarly, since 3k square plus 4k plus 2 greater than 1 for all k belongs to n, what we can say? We can say that p square plus 2 is a composite number in this case also. Yes, Afroz, do you have any question? Afroz? Okay, So I hope you understand how to solve this question. So do you have any doubt, anyone? So what we have done here, since p was a prime greater equals to 5, we have taken the form of p as residue class, as the element, as the element of residue class of 3. That means p can have 3 form at most. Okay, so 3k or 3k plus 1 or 3k plus 2, 3k plus 1, 3k case, this case we cannot consider because p is a prime. So we have to proceed with 3k plus 1 and 3k plus 2, and proceeding with those cases, we have seen that p is a p square plus 2 is a composite number. So let's try another question. So it is saying that question is, let n greater than 4 be a composite number, then n divides n minus 1 factorial. Okay, so this is the thing we need to show. So what we have to show here then? N greater than 4, strictly greater than 4, this is a composite number. So since n is a composite number, by definition of composite number, n equals to a times b for 1 greater than ab, less than a. Okay, so this is from the definition of composite number. Now what it is asking to show, n is dividing n minus 1 factorial. So how to show it? Now see, where does ab belongs? ab will be some integer inside, in between 1 and n. ab cannot be 1 and cannot be n. So a and b are one of the integers 2 up to n minus 1. So therefore ab, where does it belongs? It belongs to the one of to this set 2 3 up to n minus 1. No one of a and b can be n, because if someone is n, then other one has to be 1. That is not possible. That is not the definition of composite number. So a and b will be one of these 2 up to n minus 1 factorial. Now here we can consider two cases. One case is if a equals to b. So if a equals to b, then we can write n as a square or b square. In this case we call n to be a perfect square. And in last class I have introduced the definition of perfect square, which was like, if you can write n to be some integer, square of some integer, then we will call that to be a perfect square. So we will divide this question in two cases. One is first case is when n is a perfect square, that is n equals to a square, a equals to b here, and another case is a not equals to b. So when a equals to n equals to a square, then what we will do? So here a belongs to 2 3 up to n minus 1, and so now a belongs to this, and to a this is less than a square. So what I am trying to show is, a square has to divide n minus 1 factorial. Now since a is inside this set, I mean a is inside this set, then a will divide n minus 1 factorial. It is clear, because a is one of those integers. N minus 1 factorial, what it is? It is equals to 1 into 2 up to n minus 1, product of these n minus 1 many element, and a is one of these integers. Therefore a will always divide n minus 1 factorial. What I want to show? Want to show that this product 1, 2 up to n minus 1, it will have more than one copy of a. A is already there, so there is no doubt that a is dividing n minus 1 factorial. But we need to show that not only a but a square also dividing this factorial case. Now we are counting in some way that I mean, if we can show that c times d, this divides n minus 1 factorial, then we can say d divides n minus 1 factorial and also c divides n minus 1 factorial. This is the thing we are trying to show. Now a belongs to 2 up to n minus 1, so from here what we can say, 2 times a, that is obviously less than a square, less equals to a square. So that means a square, which implies 2 times a is also, since a square is equals to n, so n minus up to n minus 1, because okay, since 2a less than a square equals to n, therefore 2a will also belongs to this set, and therefore a into, and a is not equals to 2a, right? A is not equals to 2a, so they are two distinct numbers, both of them lies in this set. Therefore a times 2a, this will divide n minus 1 factorial. So what we are doing, we are saying that a is an integer, I mean a is an integer in this set. It's okay. Now we want to find another copy of a which will also belongs to this set. We are saying that 2a is a larger number than a, I mean a and 2a are two distinct number. Now since a is greater equals to 2, therefore 2a is less equals to a square. I mean if 2a equals less equals to a square, then 2a will also lie in this set, and since 2a is lying in this set, therefore a times 2a, this is dividing, a is also dividing n minus 1 factorial, 2a is also dividing n minus 1 factorial. This will imply what it will say. So this gives 2 times a square is dividing n minus 1 factorial, and hence a square is dividing n minus 1 factorial. So since what is the conclusion we are taking, a square is dividing 2 a square and 2a square is dividing n minus 1 factorial. So from these two we can conclude a square is dividing n minus 1 factorial. So that means that is n is dividing n minus 1 factorial. So this is the case. We are done in this case. Now another case is left. N equals to ab with a something if n is not a perfect square, I am saying n equals to a times b, where a is less than b. You can take b also less than a, but what is my main motive to say here is that a and b are two distinct integers, and since they are two distinct integers, someone will be less than some other one. So here I am considering A is less than B and n is the composite number, has the form A times B. Now here also AB belongs to this set 2 up to n minus 1, and since they are distinct, they will appear in the product. Both of them will appear in the product. Therefore both A and B appears in n minus 1 factorial equals to 1 times 2 times 3 up to n minus 1. So therefore, or thus A times B is dividing n minus 1 factorial. So why I am writing, from this statement A and B both are in this set. From here, why can we write that AB is dividing n minus 1 factorial B? Because in this product there is somewhere sitting A and somewhere sitting B. So since A times B is present in this product, therefore A times B is dividing n minus 1 factorial. So in this case also, okay, so we are done, and AB equals to, this is exactly equals to n, therefore n is dividing n minus 1 factorial, and we are done. So you may not consider these two cases differently, but for the clarity or for the clarification, if you consider these two cases separately, it will be better to understand, because this case one is something difficult rather than this case 2, because here we can consider two distinct AB, and this distinct AB will appear in one of the product, inside that product of 2 up to n minus 1. But if you have n equals to only a square, then A is appearing in the product in the product n minus 1 factorial, but another copy of A has to be present there. So for that we have considered that element 2A, and we have shown that 2A is also belonging to this set 2 up to n minus 1, and therefore A times 2A, these are two distinct elements which are appearing in the set 2 up to n minus 1, and hence it will divide, 2A square will divide n minus 1 factorial. Now since 2A square is dividing n minus 1 factorial, and A square is dividing 2A square, therefore we can conclude A square has to divide n minus 1 factorial. So in these two cases we can prove this question. So these two questions were from prime numbers. Now let's do solve some problems from the congruence relation. So I would like to recall some things. So we will recall first some theorems and properties we have seen in the lectures. So what was the definition of A congruent B? It was A is said to be congruent to B mod A integer n if A minus B equals to nk for some k belongs to Z. That means n will divide, if n divides a minus b, then we say that a is congruent to b mod n. This was the definition. Then we have seen that if a is congruent to b mod n and c is congruent to d mod n, then we will have a plus c or plus minus c congruent to b plus minus d mod n. Also we have a dot c congruent to b dot d mod n. These are the some basic properties of congruence. Then we have seen that very particular case, a times k, if here this is a 1, this is a 2, and we also have seen a power k congruent to b power k mod n, and more generally f a congruent to f b mod n for any polynomial f. So these are some basic theorems and properties of congruence we have seen in the lectures. So let's try some similar kind of theorem. Here we have see in this second relation, congruence relation, it is saying that a dot c congruent to b dot d mod n, right? Here take c equals to d. If you take c equals to d, then what we can say, ac congruent to bc mod n, right? So you can say this one is, if you take c equals to d and then apply this property 2, then you will get ac is congruent to bc mod n. So the statement will be if a is congruent to b, then for any integer c, ac is congruent to bc mod n. But if I try to ask whether the converse relation will also hold or not, if so, you are given ac is congruent to bc mod n. Can you give me any relation between a and b, any congruence relation between a and b mod n or not? We are trying to find that find the answer of this question. So keep in mind that we have, if a congruent to b mod n, then ac congruent to bc mod n for all c belongs to j. This is the conditions we have. So from 2 we are getting this one. But if I want to ask you, given, if I want the converse relation, that means given ac congruent to bc mod n, is there any congruence relation between a and b? Whether a is congruent to b mod n, we can say it or not, or a congruent to b mod some another integer which is related to n. So this is the question we want to find. So in this direction we can have the following theorem. What is that? This is saying some theorem, you can say, if ac is congruent to bc mod n, then a is congruent to b mod not mod n, but it will be mod of n by d, where d, what is d? D equals to GCD of, sorry, not C, GCD of C and n. So in the very basic theorems, what we get? We get that given A congruent to B mod n, what that will imply AC congruent to BC mod n for any C. Now I am asking the reverse. If AC is congruent to BC mod n, this is the given statement, then can we get A congruent to B mod n or mod any integer? So the answer is not always mod n, but not only mod n, but we also can get A congruent to B mod n mod D. Okay, where D is the GCD of that C and n. Now this is some kind of converse of the previous statement, and let us try the proof. So this given condition is AC congruent to BC mod n. So by definition, what does it imply? This implies AC minus BC equals to Kn for some K belongs to Z, and this implies C times A minus B, this is equals to Kn. Now D equals to GCD of C comma n, so D divides C and D divides n, therefore what we get from this relation, C by D times A minus B equals to n by D times K. Now this is an integer, this is also an integer, so therefore what we can say is that R times, I mean this is an integer, say R equals to RC, and this is equals to S, say R, then we have R times A minus B equals to S times K. So this implies, and GCD of RS is 1, so S divides A minus B, this is since GCD of RS equals to 1. So S is dividing A minus B, and what is S? S equals to n by D. So this implies n by D divides A minus B, and hence A congruent to B mod n by D. So this is the straightforward proof for this, and this gives us some kind of converse of our previous result. And then let's try some another theorem. Okay, so any doubt in this statement? Any doubt? Okay, so let's solve another theorem. So this theorem is also very similar to the previous one. Let's write the statement first. If AB congruent to CD mod n and B congruent to D, this is mod n, with GCD of B comma n, this is 1. Then we have, what we have? We have A is congruent to C mod n. What is the proof? What is the statement saying? AB congruent to CD and B is congruent to D here. This is also some kind of converse of the of this statement. So here we were from taking A congruent to B, C congruent to D, we were getting AC congruent to BD. Now what is the condition given? AC congruent to BD with B is congruent to D. Then we are checking whether in which condition A is congruent to, not here. So here we are taking AB is congruent to CD. This is we are taking, and also taking B is congruent to D. Then we are asking under which condition A will be congruent to C. So the required condition is GCD of Bn has to be 1. Then we can say CA is also congruent to C. Okay, let's prove it. So a given statement was AB congruent to CD. Since AB congruent to CD mod n, we have AB minus CD equals to NK for some K belongs to Z, and also since B congruent to D mod n, we have B minus D equals to n times R for some R belongs to Z. Now now take this relation. And multiply both sides by this. We can write it as AB minus BC. Add minus BC and then subtract minus BC. Adding BC, then subtracting BC, and then CD. We are writing CD as it is equals to NK. We can write it again as B times A minus C plus C times B minus D. This is equals to NK. Now see here, B minus D, that was equals to NR. We can substitute here. That will give us B times A minus C plus CNR equals to NK, and it will give us B times A minus C equals to N times some K prime. And K prime has some, K prime will be exactly equals to K minus CR. And there, now in this equation, okay, K prime belongs to Z and K prime equals to exactly K minus CR. Okay, now given condition was GCD of Bn equals to 1, and therefore we can use Euclid's lemma here, and we can conclude, since GCD of Bn equals to 1, using Euclid's lemma, we can conclude what we can conclude. So here we can say n is dividing, from this equation we can say n is dividing b times a minus c. Since GCD of b and n equals to 1, by Euclid's lemma we can say n is dividing only a minus c. N is dividing a minus c. Therefore, a is congruent to c mod n. So this statement is saying n is dividing b times a minus c, and then by given condition GCD of Bn 1, and then you use Euclid's lemma, it will give you n is dividing a minus c. So therefore we are done. So let's solve some problems to see how this congruence relation. So these are the some theorem kind of very familiar, similar to those theorems we have seen in lectures. Now we will solve some questions related to that congruence relation. First, let's try with this problem. Find the remainder when 2 power 50 is divided by 7. So this is one of the most familiar kind of question. Usually we ask in usually we can see in the exams. So not only 2 power 50, they can give you some sum of some powers, and may ask that find remainder when this term is divided by some large integer. Then you have to use the theory of congruence to find those answers. So here it is saying that divide 2 power 50 by 7 and then tell me what is the remainder. So we will use the theory of congruence here to find the remainder term. Now 2 power 50, what we do in this case, we generally okay, 4 you are saying, then can you tell me the procedure how you solve?
Ma'am, firstly we take 2 raised to power 3 is congruent to 1 mod 7.
Yes, 2 power 8, that is 2 power 3 means 8, and this is congruent to, this is equals to 8 and this is congruent to 1 mod 7, and
then take power 16,
then
2
2
raised to
power
power
3
3
whole power
16.
16, that will be congruent to 1 power 16 mod 7. What is
Yes.
the theorem we are using here? We are using if A congruent to B mod n, then A power k congruent to B power k mod n, right? This is the exactly theorem we are using. So using this we can say this, and therefore 16 times 3 means
2 power 48 is congruent to 1 mod
2
7.
power 48, this term is 2 power 48 into 2 power 2. If you multiply both sides by 2 square, then you will get 1 into 2 square
4
mod 7. what is the theorem we are using here? Here we are using A congruent to B and C congruent to D, or you can say A is congruent to B mod n, that will give you AC is congruent to BC mod n, right? So what we are using here, A congruent to B mod n, that will give us AC congruent to BC mod n. This is the theorem we are using here. So from these two we can conclude 2 power 50 congruent to 4 mod 7, right? Okay, this was one of the very familiar kind of question. Now let's try another question. What will be the remainder when 1 power 5, 2 power 5, 3 power 5 up to is divided by 4. Okay. So for your reference, I would like to say that the problems I am solving here, I am mainly following M button exercise. Okay, so if you see the exercises from the book Elementary Number Theory by David M. Barton, then I hope you have seen it, and if you solved it, then it's very fine. And I am trying, I am picking up some problems from exercise of that book and trying to solve it. Okay, you can do it by yourself also. There are plenty of exercises and they are also very nice. So if you wish, you can do all those, and these problems you can find mainly there. Some problems may not be there, but most of the problems are inside that book. Okay, now let's do this question. So can you try how to solve it? Kamaljeet, will you say anything? You can say if you. What we will do here, so we know the theorem A congruent to B, C congruent to D, then A plus B, A plus, we know all these theorems. We know all these things, right? We will use it, we will use this one also. Mainly using 1 and 4, we will solve this problem. Okay, so now see, we are dividing it by 4. So how many remainders we can have by dividing 4? At most 3, 0, 1, 2 and 3, right? So any consecutive 4 integer you take, you will get 0, 1, 2, 3. For any consecutive 4 integers, you will get all these 3 remainders. So let's clump this 1 power 5 plus 2 power 5, this 100 many, this term is addition of 100 elements of the form A power 5. We can write it as 1 power 5 plus 2 power 5 plus 3 power 5 plus 4 power 5 plus 4 plus 1 this power 5 up to 4 plus 4 power 5. In this way we can write it as nth term will be 4 plus n power 5 plus 4 plus n plus 1 power 5 in this way up to 100 power 5. Now these are 4 consecutive integers, power of 4 consecutive integers. This in this also power of 4 consecutive integers, here also power of 4 consecutive integers. Now so for let's for any term of the form 4 plus n whole power 5, this is congruent to n mod 4 plus n plus 1. I mean we should write it, we should not write it in this form. What we should write here is that plus 4n plus 1 whole power 5 plus 4n plus 2 whole power 5 plus 4n plus 3 whole power 5 plus 4 into n plus 1 whole power 5. This is the nth row plus up to 100 power 5. There will be some here, it will be 96. Okay, so now see 4n plus 1 congruent to 1 mod 4, 4n plus 2 congruent to 2 mod 4, 4n plus 3 congruent to 3 mod 4, and 4 into n plus 1, this is congruent to 0 mod 4. So this is, I mean this was the nth entry, and for any integer n, therefore if you take those 4 addition of 4 consecutive terms, then you will get only these as a remainder. So therefore what we can say, thus 4n plus 1 power 5 up to 4 into n plus 1 power 5, this is congruent to 1 plus 2 plus 3 plus 0 mod 4, that is 4n plus 1 power 5 up to 4 into n plus 1. This is right hand side is 4, that means again congruent to 0 mod 4. Thus, and this is for all n belongs to natural numbers union 0. So thus 1 power 5 up to 2 power 5 4 power 5 plus 5 power 5 up to 8 power 5 up to 96 power 5 plus 100 power 5. This is all these are congruent to 0 mod 4. So what will be the remainder of the given expression when dividing it by 4? That is 0. That means that sum of fifth power of all natural numbers up to 100, that will give you remainder 0 when it is divided by 4. let us use induction and congruence together in some questions to get a required result. Okay, before that let's do another, let's solve another question. So you just tell me, because okay. Prove that 53 power 103 plus 103 power 53 is divisible by 39. So can you tell me this proof? Can you try it? Ganga or Tenmoji or Kamaljeet? So what it is asking to show? It is asking, when we are dividing this sum by 39, then we can get the remainder 0. We will get the remainder 0. So what does it mean? Okay, let's give you some further hint. So 39 equals to 3 into 13. So if 39 divides some element, then what we can say from this given expression? This is the primary decomposition of 39, or sorry, prime decomposition of 39. So Kamaljeet, can you tell me this answer?
Ma'am, can you repeat question?
The question is prove that 39 is dividing this 53 power 103 and plus 103 power 53. And I am giving you further hints that 39 has this prime decomposition 3 into 13. So if some element is dividing, if 39 is dividing some element, this is equivalent to, so 3 is dividing that element and 13 is also dividing that element, right? So if something has prime decomposition and that element, say n has prime decomposition p1 power k1 up to pn power kn, and n is dividing some element, then each prime should divide that element. Each prime power should divide that element. This is the thing I am telling you. Yes, both the terms, both terms means this one. This one also should, if we can show that 3 is dividing this one and also this one. Again, if we can show 13 is dividing this one and this one, then we can say that 39 is dividing this whole term, right? So now use the theory of congruence to show that to show that 39 divides 53 power 103 plus 103 power 53. It is equivalent to show 3 divides 53 power 103 plus 103 power 53 and 13 divides 53 power 103 plus 103 power 53. Now use theory of congruence to show this one. Now 53 mod 3, what is that? 53 congruent to what mod 3? If you divide 53 by 3, what will be remainder? Just tell me.
That will be 2.
2 mod 3, and 2 is congruent to minus 1 mod 3. Why I am doing that? Because minus 1, if you take some power, it will give you either 1 or minus 1. So 50, that will imply 53 power 103. This is congruent to, since the power is negative, again minus 1 mod 3. And what will be the remainder when we divide 103 by 3? One, right?
Yes, 1.
Why minus 1? Because 2 is congruent to 2 minus 3. I mean, you can add, when you are taking mod n, some element is say k is congruent to, or what shall I say? So 53 is congruent to 2 mod 3. You can say 53 is congruent to 2 plus 3k mod 3 for all k belongs to z, because 3 is always divides 3k. So this 3k will not matter if you add 3 or if you subtract 3 or some multiple of 3. So 53 will give us remainder 2, and then we are taking, this is congruent to 2 minus 3 mod 3, and therefore 2 minus 3 means that is 1, right? 2 minus 3 is minus 1. Therefore we are saying 53 is congruent to minus 1 mod 3, and 103 is congruent to 1 mod 3. That will give us 103 power 53. That is also congruent to 1 mod 3. Now add them and take modulus. What it will give? Thus 53 power 103 plus 103 power 53 congruent to minus 1 plus 1 mod 3, and this is giving us 103 power 53 congruent to 0 mod 3. That is 3 divides 53 power 103 plus 103 power 53. Similarly, what you have to show? You have to show 13 is also dividing this sum. So similarly, if you divide 53 by 13, what it will give you? 1 mod 13, 52, and therefore 53 power 103 congruent to 1 mod 13, and 103, if you divide it by 13, what it will be? What will be the remainder?
Minus 1.
Again minus 1. So that will give us 103 power negative power. We are taking odd power, therefore congruent to minus 1 again mod 13, and this will give us 53 power 103 plus 103 power 53 congruent to 1 minus 1, that is 0 mod 13. So 3 is also dividing that sum, 13 is also dividing that sum. Hence 3 into 13, that together will divide that term. Thus 39 divides 50 from here, from this and from, okay, hence we can conclude. Okay, so these type of questions may come in exams. Or now let's try some question in which we will use the principle of mathematical induction I have introduced in the very first class, and also theory of congruence. Okay, establish that for an odd integer a is a odd integer. We have a power 2 power n, that is congruent to 1 mod 2 power n plus 2. This n is for any integer n greater or equals to 1. Okay, I mean for any natural number n. So how to show that? What are the given condition here? Given condition is an odd integer a, that means a is an odd integer. Then for any natural number n, we will have this congruence relation, a power 2 power n, that is congruent to 1 mod 2 power n plus 2. So since it is saying that it is asking to prove it for any natural number, what is the best method in number theory for proving such kind of condition? Is the
Mathematical
use
induction.
of mathematical induction. So in that tool there are two steps. First one is base case, that is show it so that this is true for n equals to 1, and in induction step assume that it is true from 1 up to some integer m. Assume that statement is true for all the integers 1 up to m. Then so that that statement is also true for the integer m plus 1. If you can show this one, then you can conclude it is true for any natural number n. So let's try the proof. So what is the statement here? The statement we denote it by Pn. This statement is a power 2 power n congruent to 1 mod 2 power n plus 2. So to prove the base case, what we have to show? We have to show for this is Pn is true for n equals to 1. Let us check that first. Base case is so if we take n equals to 1, we have to show for any odd integer a power a square is congruent to 1 mod 2 power 3. That means a square is congruent to 1 mod 8. So this can also be a this base case itself can be a question of 2 or 3 marks. Okay, so since I am proving the whole questions, I am not dividing it in two parts, but in exam you can find this base case can also occur as a exam question. Okay, So let's try it first. Want to show that for odd integer a, 2 square a square congruent to 1 mod 2 cube means 8. Okay, so can you show this one? So it is asking that for any odd integer a, you have to show when it is divided by 8 will give us the remainder 1 when it is divided by 8. So what which forms of a you are expecting to be considered here? I mean a is odd integer, so what is the form of a when we are taking in the residue class of 2? What will be the form of a? Tell me first, then, or otherwise you just tell me which residue class we should consider so that we can get a form of a square giving residue 1 when divided by 4. I mean which form of a you should consider here, given that a is odd. Shall we consider a is of the form 2n plus 1? Will it give us any answer? Okay, this is the first thing we can consider. Since a is odd, we can always take as a equals to 2n plus 1 for some integer n. But in that case, if you proceed further, I mean if you take n square, and then can you get some can you get always say that remainder will be 1 when divided by 8? No, right? Because if you take a equals to 2n plus 1, take a square, it will give you 4n square plus 4n plus 1. So when you are dividing by 8, you don't have any clue whether remainder will be 1 or not. So 2n plus 1, then you have to take another form of n also, so that will be complicated. So if you take a of the form 2n plus 1, it will not give you the answer directly. So what is the next guess you should consider? So 2n plus 1 means residue class of 2. Then you can say take the residue class of 3. I mean a is of the form 3n or 3n plus 1. 2n plus 3 means that is not in the residue class, right? 2n plus 3 you can always write it as 2 into n plus 1 plus 1. That means of the form 2m plus 1. I mean in residue class of 2 only 2 remainder is possible, 0 and 1. So in this case, so you should guess intelligently you should guess, because if you take 2n plus 1, it is not giving you any any direct answer. Then if you take the residue class of 3, I mean a is of the form 3n or 3n plus 1 or 3n plus 2, you cannot always say that a is from that part, I mean you are getting 3 or 3 square 3 cube kind of. If you take a square, then also it is not giving you any direct answer. So next target should be 4n, I mean residue class of 4. Then consider the cases where a is odd. So guess should be considering the form of a in the residue class of 4. So since a is odd, A can it can be one of the following forms. So what are they? Say case 1, say let A equals to, so if you take the form of A in residue class of 4, then A has 4 many choices, either 4A or either 4n or 4n plus 1 or 4n plus 2 or 4n plus 3. Now among these 4 cases, what are the cases in which A will be odd? Only 2 cases are there, either 4n plus 1 or 4n plus 3. So we will consider here these 2 cases since the given condition is A is odd. So case 1 is take A equals to 4n plus 1, and case 2 let A equals to 4n plus 3. Now for 4n plus 3, what is A square? See, this is 16n square plus 8n plus 1. This is congruent to 1 mod 8. So this is the form where if you divide it by 8, you directly can see that this is congruent to 1. So in this case we are done. We are getting A square is, in this case A square is congruent to 1 mod 2 power 3. This is the result we are expecting to be true in our base case of induction hypothesis. So when A has this form, we are done. Now let's see this case. Here also similarly 16n square 24n plus 9, that is A square congruent to, if you divide it by 8, that will give you remainder 1 mod 8. Mod 8 means mod 2 power q. So in this case also we are done. Thus Pn is true. Here we should write m because we already have used the notation n before. Pn is true for n equals to 1. So we are done in that base case, that is when A is an odd integer, and when A is an odd integer, then A square is congruent to 1 mod 2q. So base case is done. This was the condition we tried to show, and we have shown this condition in these 2 cases, case 1 and this case 2. So base case is done. Now next step is induction step. So what we have to assume here, let Pn be true for n equals to 1 to up to some integer a. Okay, though we will mainly use that Pm is true, but it is always safe to consider Pn is true from 1 up to m. For every integer from 1 up to m. In the most of the cases we use we require only Pm to be true to show that Pm plus 1 is true, but in some cases you can find that it will be better if you consider that Pn is true from 1 up to m, every integer from 1 up to m. So let's see what we will use here. So here we are taking Pn to be true for n equals to 1 up to m. Since Pm is true, what we can say, thus what was the statement of statement Pn? A power 2n, thus a power 2 power m that is congruent to 1 mod 2 power m plus 2 since Pm is true. Now what shall I say? So a power 2 power m is congruent to 1 mod m 2 power m plus 2 by the definition. Therefore we can say we have a power 2 power m minus 1, this is divisible by 2 power m plus 2. Therefore a power m, what was that? We'll have the form 1 plus r into some 2 power m plus 2 for some integer r. This is the by definition of congruence. Now to get a power 2 power m plus 1, how to increase the power of 2 power m? If we take square both sides, then see what happen. A power 2 power m into a power 2 power m, that will give you 1 plus r into 2 power m plus 2 square. Now what is the left hand side? This is exactly equals to 2 power m plus 1. In power there is 2 power m plus 1. This is equals to 1 plus 2r 2 power m plus 2 plus r square 2 power 2 into m plus 2. Okay. Now this is left hand side. This is congruent to 1 plus, what is this term? This is congruent to, when we are taking it under mod 2 power m plus 3, what it will give us? Congruent to, so we can write it as this term, we can write it as r times 2 power m plus 3, right? And this term is equals to r square 2 power 2m plus 4 is always divisible by 2 power m plus 3. So you can see here, first term is congruent to 1, but second term and third term are congruent to 0 mod 2 power m plus 3. That is a power 2 power m plus 1, this is congruent to 1 mod 2 power m plus 1 plus 2. Hence Pn is true for n equals to m plus 1. So assuming Pn is true from 1 up to m, we have shown that Pn is true for n equals to m plus 1. Therefore, by principle of induction hypothesis, Pn is true for all n belongs to set of natural numbers. Therefore, the statement we are trying to show is always true for any natural number n. Okay, so we have shown it. Okay, so let us stop today because